hopefully it won't blow your mind today, but bomb. We'll first do flame calorimetry. We won't do bomb. Bomb sounds cool. It's not what you think. Okay, so don't relax. All right, we're not going to make bombs. So trust me. I don't trust you with that. All right. What's going to happen is I just said the word bomb on my podcast or my YouTube, and then the government of the United States of America will find that, and they'll be like, "Oh, check this guy out. What's his terrorist?" Could happen. Never know. This is what it looks like for flame calorimetry. That's what we're going to focus on first. Okay, flame calorimetry. This is what we're going to do tomorrow. So it's going to actually look identical to this. You'll see tomorrow. We are going to have some type of flame or some type of fuel source down below here. Okay, something along this line here. Now this one's got a big can that's kind of surrounding it. I know your diagram's a little bit smaller. I get that, but you're going to have some way of basically kind of capturing the heat in there. Okay. Tomorrow we'll use a candle, and we're going to put it in a coffee can. So that's going to be kind of the surrounding to kind of keep the heat in. You're going to lower this this other can here, small can. Usually we consider that to be aluminum cans. Okay. If it doesn't say, we're going to assume it's aluminum can or aluminum cup, basically. Sorry, aluminum cup. And we're going to lower this on top of the flame there, and we're going to calculate basically what's going to happen here. Well, the fuel is going to give off energy, right? Yes. E lost. Yes. Yes. What's going to gain the energy? The water. But in this case, what else gains energy here, do you think? Take a look at the system here. What else do you think is going to gain some energy here? The metal, the aluminum cup. Yes. So not only does the water gain energy, but so does the aluminum cup. All right. So guess what? You guys pretty much know how to do this already. Yeah. This is not going to be too tricky. You're going to put this the ring clamp stand, or basically this ring stand here, and it's going to have just a little wire through it. It says clothesline wire. It doesn't really matter, but it's going to be suspended above here, above this flame here. We're going to fill that up with water. We're going to stick the thermometer in there. We're going to measure the temperature, basically how much it goes up by. If we measure that temperature that it goes up by, okay, we can assume also that the can is going up by that much temperature, MC delta T, and we're going to be able to figure out, for example, once again, the molar enthalpy of this fuel down here, for example, or any other thing that we might want to consider there. So that's what we're going to do. As the fuel burns, it releases heat. Most of the heat is absorbed by the water. However, some of the heat is also absorbed by the metal can. All right, so we just talked about that. This kind of moved over here, so I apologize for that. What happened here? Oh, let's see here. Well, first of all, if we want to calculate delta CH, the molar enthalpy of combustion, because that's what you're calculating, right? Combustion of that fuel, whatever it happens to be. This got moved over here, guys, so I don't know if I can move this over, but that should be over here, kind of thing. Let me just, I don't think I could fix that right now real quick, but here, let's do this. So E, well, you guys have it on your sheet anyway, right? So it should be okay. E gained, of course, equals E lost. Don't forget the negative there. This will be your N delta, well, CH, I guess, in this case here, combustion, yes. And on this side here, what's gaining the energy? Like I said, MC delta T, and also MC delta T, and I ran out of room above, so I'll just do it below. There is a can that's involved, or the metal, and there's also some water that's involved in this case here. Okay, so both of those things are gaining energy, yes? All right, so whichever way you want to have it there, or the metal in this case, whatever. Okay, so that's what we're going to look at today. This is not anything more complicated than what we've done before. Okay, we're just adding an MC delta T on, that's it. Okay, so for example, here's a methanol burner is used to heat up water inside a tin calorimeter. Use the following observations to calculate the heat of combustion for methanol, that is methanol there, CH3OH, in both kilojoules per mole and kilojoules per gram. So we are going to change this a little bit. We're going to also talk a little bit about kilojoules per gram as well. And you're going to do this on your lab tomorrow, so pay attention here. All right, so here we go. We have all these calculations here. Okay, so unfortunately, you guys can see that there. You're going to have to do some work with me here, find some space there for this. So here we go. I'm going to scooch this up here. You guys have that on your sheet, so you should be fine here. Okay, so a couple things. First of all, We're going to go with E gained. You guys can copy this down, of course, because you need to. So we want to calculate delta CH, right? The change, the heat at molar enthalpy of combustion. And over on this side here, of course, we're going to do MC delta T and MC delta T. Okay, twice. One's for the water, one's for the, in this case, water and the metal. Okay? Now, N. Well, let's take a look at what we have here. Let's go back up to the, well, we don't have to go back up to the top, but you see right here, for example, it says the mass of the tin can is 70.32 grams. The mass of the tin can in the water is 195.49 grams. From those two measurements, you get quite a lot of information from that. First of all, you get the mass of the tin, right? Mass of the tin can is 70.32 grams. So I'm going to put that here. Now, it depends on how you wrote this down here. Don't forget, we probably, if we want kilojoules per mole, we probably should be using kilograms, yes? Yeah? So the mass of the metal here, the tin can, weighs 70.32 grams. So we're going to change that to 7032. I'm not going to have enough room here, guys. Just give me a second here. Where can I put this here? Plus 0.07032 kilograms is the mass of the metal, okay, the tin can. C, what's the C for tin can here? Well, we're going to look that up in your data booklet. What's the specific heat capacity of tin there, guys? Somebody, quickly. 0.227 joules per gram degree Celsius. And how much is it heating up by? Well, once again, we have to assume that any energy we're putting into the water, we're also putting into the tin can. So if the water goes up by 19.8 to 42.6, we have to assume the tin can is doing the same. Both energy, it's not specific for, you know, if the water's going up, the tin can has to be going up as well. Okay, so subtracting those two there, let's see, 42.6, the final, minus the initial, which is 19.8, and we get 22.8 degrees Celsius. Okay, 22.8. Okay, so if the water is going up by 22.8, we have to assume, of course, that the tin can is going up by the same amount. Okay, water. How much water do we have here? Okay, that is the question. So don't forget, water, of course. Mass of the tin can and the water is 195.49. That's the tin can and the water. But we just want the water, of course. So we're going to subtract the mass of the tin can. Okay. So if we subtract the tin can, which is 70.32, we get 125.17 or 0.12517 kilograms. 4.19 here again. I'm going to skip the units if that's okay, just because I don't have enough room to write them. And the delta T, of course, once again, 22.8. Okay? So that's the mass of just the water. Mass of the tin can, we got to treat those separately because they do have specific heat capacity differences. All right? On the other side, we have delta, or N, I should say, N delta CH here. What is N going to work out to be here? It tells me that, what does it say here? The initial mass of the methanol burner was 221.5, right? 221.5. After I do this experiment, now it only weighs 220.88. So we're going to subtract those two numbers. 221.5 minus 220.88. And it's 0.62 grams of methanol is how much I burned. Yes? Okay? So that's going to go in here. 0.62 grams. And delta CH. Okay? Over, of course, the molar mass, because we need to change that to moles, yes? So what's the molar mass? Well, it's methanol. It tells you up at the top there, it's CH3OH, okay? So I need what? 1 carbon. Let's take a look here. 1 carbon, I need 4 hydrogens, and 1 oxygen. So 32.05 grams per mole. 32.05 grams per mole. Okay. My suggestion when you go to do this question is that perhaps you maybe do all this part first, the left side first, add all those numbers up, multiply and add those up. So let's see, 0.12517 and 4.19 and 22.8, and we're going to add to that 0.07032 times 0.227. That is 10, right? 0.227, yes. And 22.8. And on this side total here, I get 12.32. This would, of course, be in kilojoules. Or sorry, kilojoules, not kilograms. Kilojoules. And on this side here, I have my 0.62 divided by 32.05 grams per mole, grams delta CH. Okay, and when we divide those two, okay, so I'm going to divide it by my negative 0.62 divided by 32.05 here, and I get as a final answer delta CH is a negative 637 kilojoules. I think that's probably all we'll be able to use for significant digits, perhaps. Let's see. No, maybe we can use 4. So maybe 37.0. I'll have to double check that here in a sec, but 37.0. Let's see. 22. Well, no, the temperature is only 3 there, so 3637. Okay. Kilojoules per mole. Okay. Don't forget, you're calculating the molar enthalpy, so you're looking for kilojoules per mole of that. All right? Is that okay so far? As far as where they got all the masses from and whatnot? Okay. So, mass of the tin can, 20.32, that was this right here. Okay. There's my tin, there's my tin, there's my tin. It's got to go up by the same temperature. Okay. Where do I get the water from? Well, it was the tin can and the water, and then of course subtract just the tin can will give you the water. So that's where I got this one from. Specific heat capacity of water, that's how much the temperature went up by for the water. Okay. Over here, I had 0.62 grams. That was the initial weight of the burner minus the at the end, when you're done burning it, the weight after. And we're going to do the exact same thing tomorrow, guys. This is exactly what we're going to do tomorrow in the lab. Okay. So you weigh it initially, you weigh it at the end. The difference is how much fuel you've burned. Okay. All right. So 0.62 grams I used. Molar mass. That'll tell me how many moles I have here, of course. Right. When I divide those two, and when I divide those two, I get negative 637 kilojoules per mole for methanol. Okay. If I want to change it to kilojoules per gram, how am I going to do that? Well, probably the easiest thing to do is say, okay, well, this is a negative 637 kilojoules per 1 mole, right? 1 mole, though, of methanol, look, methanol has a molar mass of 32.05 grams per mole, yes? That's periodic table. Calculate 1 carbon, 4 hydrogens, 1 oxygen. So for every mole of methanol, it weighs 32.05 grams. So can I not just say this would be the same as saying negative 637 kilojoules for 32.05 grams? Is that not the same of methanol? 1 mole of methanol is 32.05 grams. Those two are equivalent to each other. We're specifically talking about the methanol. All right. So if I divide these two, kilojoules over grams here, if I divide those two, I get a negative 19.9 kilojoules per gram. That would be my other option here. So those would be your two answers for this. So for every gram of methanol that I burn, I get 19.9 kilojoules of energy released. Okay. So kind of follow that, I guess, and if, once again, hopefully we'll have some time here today. If not, come back at extra help. I'm going to give you guys a worksheet on that today, obviously. But just double check that, and like I said, if you have any questions, let me know. Okay. All right. You can set it up fancier than that if you want. So you could have put, well, 1 mole of methanol is 32.05 grams, 32.05 grams per mole. Cross those out. You're going to do the same thing, though. Okay. Next here, and like I said, hopefully we'll have some time to practice some of those questions today here. We're going to talk about bomb calorimetry. Bomb calorimetry. This is what a bomb calorimeter looks like. Okay, it's not a bomb that's taking place. It is kind of the system or the setup that we have for this. This is what a bomb looks like. It's got a thermometer stuck into it. It's basically like the calorimeters we used the other day. Okay, except it's made out of metal, not styrofoam. It's got a magnetic stirrer, so it's got a stirrer in there. It's all concealed. It's all enclosed. The water's inside of here. You put the reactants into there. Okay, and it basically takes care of itself, kind of thing. It's a, the temperature you can read there. It's got water in there. You put the reactants in there. It's got a stirrer, like I said. It's got a wire for ignition to do that combustion reaction or whatever the case might be. So it is basically a steel container, or a container that takes the place of our styrofoam cup. It's all encompassing. The difference is, though, where our styrofoam cup doesn't really absorb or release energy, in this case the metal container does take in energy, because some of that heat is going to be transferred to things like the container itself. The stir rod is made out of metal. Anything else in here is going to absorb some of the energy. So we need to account for all that stuff. Okay. So the combustion reaction takes place within an inner metal chamber, the bomb, which contains pure oxygen. Okay. To measure heat precisely, you must know the specific heat capacity of the calorimeter. The heat capacity is generally measured in something called kilojoules per degree Celsius. So kilojoules per degree Celsius. So when you see that, okay, when you see those units, kilojoules per degree Celsius, you are going to know that basically you're dealing with a bomb calorimeter in that case. Okay. Okay. Now this here, I think yours is fine here. Mine somehow got that in there. Bomb calorimeters don't involve little c. Okay, so listen, and we'll show you the formula here in a bit. They don't involve little c, so there's not a specific heat capacity for the water, for the metal container itself, etc., etc. We usually could refer to it as a big C. Okay, and I think that's coming up here yet, so we'll just be patient. The heat absorbed by the calorimeter during combustion fuel can be found by the following. Q equals C delta T. Remember, it's going to be the same thing we did before. This is, of course, kilojoules. This, of course, is kilojoules per degree Celsius, big C. And this is degrees Celsius. Okay? When you see big C, capital C, you will know it's a bomb calorimeter question. Okay? They're actually probably even easier than the other ones. All right? So I'll show you what that looks like here in a second. Okay? Q, of course, is the energy, kilojoules. Kilojoules per degree Celsius for big C and delta T. Okay? The general equation for delta for this kind of bomb calorimetry looks like this. Okay? Geez, I thought I had another slide in here, but apparently not. I must have taken it out. Okay. Let's just go back here for a second. Okay. If you are doing this type of bomb calorimeter, like we just finished flame calorimetry, you could do that with this. You could. However, How many MC delta T's are you going to have for this? Probably quite a few for a bomb calorimeter, because like I said, you have to do MC delta T for the water. You'd have to do MC delta T for the steel container or the container itself. You'd have to do MC delta T for the stir rod. You'd have to do MC delta T for this metal down here if it's not the same metal. You'd have to do MC delta T for anything else in here that I may have forgotten. Okay? So you might end up doing 4 or 5 or 6 or 7 MC delta T's for this bomb calorimeter. Okay? Could you do it like that if you had all the information? Sure you could. Usually bomb calorimeters don't involve MC delta T. Okay? Usually bomb calorimeters, we cut out the MC delta T like 6 or 7 times, and we do C delta T. That's it. Okay? C is the specific heat capacity for that bomb calorimeter. So they've calculated all that MC delta T stuff for you and told you what C is. And that C happens to be measured in kilojoules per degree Celsius. Okay? So let's show you an example here. So this is what your system would look like. It's even simpler than the flame one. Here's the same stuff we did before, guys. Here's your fuel. And here's your bomb calorimeter part. Big C delta T. Is that clear? Yes? You understand? Okay. All right, so let's take a look at a question here. Okay. Naphthalene has the formula C10H8. When 1.5 grams of C10H8 is burned in a bomb calorimeter, so when you see bomb calorimeter, that's the first indication, which has a heat capacity of 8.57 kilojoules per degree Celsius. Look right here, guys. Where do you see kilojoules per degree Celsius? In a bomb calorimeter. Okay? Well, first of all, they told you it's a bomb calorimeter. Second, kilojoules per degree Celsius tells you it's a bomb calorimeter. The calorimeter increases by 7.42 degrees Celsius. There's your delta T. That's how much the temperature goes up by. Calculate the molar enthalpy, okay, et cetera, and then use your balanced chemical equation to represent that, okay? Now, there is one other thing, and I don't know what happened to these slides here, but you're going to have to write this down. In a bomb calorimeter, okay, combustion reactions, maybe I'll save that for down here, but the combustion reactions are just slightly different. Oh, for crying out loud. They are slightly different, and I'll talk to you about. There you go. All right. So just a reminder, you will have to make sure that's a liquid. You might say, is there a big deal or whatever? The answer is there is, because when we do Hess's law, which is the next part, this here, there's 2 different numbers for a liquid and a gas, so you do have to know the difference, okay? So make sure that you know that, all right? It's like I said, one of the little details you're going to have to know. I know what you're thinking. I'd sure like some practice on this, and here you go.